Good afternoon, everybody. It's my great pleasure to welcome you to this today TechTalk. I'm Tong from Department of Civil Engineering in this university. TechTalk is a series of forums and dialogues given by engineering researchers of a diverse academic background to share the insight on innovation-based topics. Our speaker today is Professor Irene from Hong Kong University of Science and Technology. Professor Low has been teaching at HKAE for quite a long time, since 1992. And she is currently a chair professor in Department of Civil and Environmental Engineering at UST. He was also appointed by Hong Kong government as Justice of the Peace, 太平绅士, in the year of 2017. Professor Low is an internationally renowned scholar and is among the first to invent the iron-based nanomaterials and photocatalytic materials for pollution control. He was a recipient of numerous prestigious international research awards and the University Distinguished Teaching Awards. He had been invited to give over 100 plenary, keynote, or invited speech at international conferences. Her lecture today, topic is about transforming wastewater into green hydrogen, an option to produce fuel for the future of Hong Kong. Please welcome Professor Low along with me. Professor Low, please.
Thank you, Professor Zhang Tong, for the kind introduction. Now, today I would like to share with you about the recent research which our research team has been exploring for 10 years. And then we find that there's a lot of interesting results. And then I would like to report to you today. I know that not many of you exactly in the environmental engineering and doing the chemistry research. So I will try to tune down the presentation in a way that most of you can understand and avoid very detailed discussion about their scientific mechanisms. Now, today, my topic is the transforming wastewater into green hydrogen. Is it an option to produce the fuel of the future in Hong Kong? Now, as you might know that for the wastewater treatment, conventionally, we have the process like the primary treatment and also the secondary treatment. And then after the secondary treatment, we will have the disinfection to inactivate or to kill the bacteria. So that is the general process we often used for our wastewater treatment today. All right? Now, for this kind of treatment, although we have been used it for so many years, but it still has many limitations. At least, right, these 3 limitations has been reported elsewhere. The first one is the presence of the pharmaceutical and personal care product. In short form, we say PPCP. You might not know that every day, right, we are often to use antibiotics because the medical doctor also give it the prescription to buy the antibiotics if you get sick. But then in our wastewater, we often find the presence of those antibiotics, we say is emergent pollutant in certain concentration. But the conventional wastewater treatment actually is not designed to treat or to remove these kind of antibiotics. So it's often present in our treated wastewater without any removal. The second problem is the wastewater treatment is a kind of high carbon emission because using the conventional wastewater treatment, we will generate the nitrous oxide, N2O, and also the methane gas, which is high greenhouse gases with the global warming potential substantially larger than CO2. So we have to remove these greenhouse gases because nowadays we talk about the low carbon emission process and try to avoid any global warming issue. The last limitation is that after we treat the wastewater, we use chlorination for disinfection. But chlorination often have the problem because after we use chlorine, we kill the bacteria, but we know that we might produce the disinfection byproduct. Disinfection byproduct is a cancer-causing substance. Although you and I don't see any issue about causing the cancer because we try to regulate the cancer-causing disinfection byproduct to certain concentration before we discharge to the water body, all right? And also, adding chlorine is chemical-intensive process, all right? So this is the current limitation. Other than this, treating wastewater involves high intensity of energy. We need electricity. We need a lot of energy consumption. But then, can we ask ourselves, is there any technology we can treat the wastewater to meet the standard as well as to produce energy rather than use energy? Is it possible? That is the question we would like to explore today. And then among the hydrogen energy, right, we want to produce, everybody wants to get is green hydrogen because it is green and it is not generated from the dirty fuel such as the coal combustion. To generate the hydrogen, we call this is gray hydrogen. But if we use the renewable energy to generate the hydrogen, then it is called green hydrogen. But generating the green hydrogen nowadays is expensive, right? Although it is good, but then nobody really produces such kind of hydrogen because it's expensive. And in Hong Kong, as you might know that, the Hong Kong government actually has a plan to develop the hydrogen. And last year, in 2024, actually, they already have this development plan with 4 core strategies, such as how to improve the legislation for the use of the hydrogen, how to set up the standard for the hydrogen production. And also, our chief executive, during his policy address last year, he particularly mentioned about the launch of the subsidy scheme for the hydrogen fuel cell for the electric heavy vehicles. And also there's a roadmap, all right, for the development and the use of the hydrogen in the coming years. And hydrogen, you might ask that, once we produce, we generate, in what way we can use hydrogen? In Hong Kong, we can identify that the hydrogen can be used for transport because we have those hydrogen vehicles. And hydrogen can be used for the mobile machinery to replace the diesel fuel because diesel fuel is high carbon emission, the fuel, dirty fuel. And then hydrogen can be turned into electricity for power supply. So there's a number of applications we can consider when we have the hydrogen produced locally. So then the question is, we need to find out a new innovative technology which can treat our wastewater to meet the treatment standard in Hong Kong and at the same time to produce hydrogen. So among many technology we consider, and then we finally, right, consider the use of the PEC, which is a photoelectrochemical process. In our research group, actually, we have rich experience of doing the PEC or photocatalysis process in the last 15 years. And then every time, you can see that, we publish the paper using the PEC to remove or degrade the organic compound. So for single function. And then we also develop the material used for the PEC or photocatalysis, such as titanium dioxide in different form, to inactivate bacteria or to kill the bacteria. And also we use the PEC in other way, is to oxidize ammonia nitrogen to nitrogen to avoid the generation of the nitrous oxide, which is greenhouse gases. And also we know that water splitting can produce hydrogen. So our research group has done this kind of research. And now the difficulty is that we need to find out common materials used as photoanode in the PEC technology, which can do all these things, to remove organic pollutant, to inactivate bacteria, to remove ammonia nitrogen, and to generate hydrogen. So is there any single materials that can do so many things together? So then that is the ultimate objective. As I said, we want to find out the materials as the innovative photoanodes in the photoelectrochemical process, which can do multifunctions, right, to remove different pollutants and produce hydrogen. And at the end, this technology can be classified as net zero emission, or even more ambitious to claim as the negative emission technology. So we start with the batch study to see whether our idea, our concept, works or not. And then if it works, then we move from the batch study in the laboratory and enlarge the scale to the large-scale continuous flow reactor and treat the real wastewater rather than the simulated wastewater. So today, right, I would like to share the findings with you and then tell you the result. So among different materials, we have been searching, and then we have to fit different criteria because we want to do multitasking, multifunctional materials. So this is just the study, the investigation desktop study to see different materials. They have different band gap. And then we want to produce hydrogen. We want to remove pollutants. And then among those different materials, we identify the potential materials, which is called the bismuth vanillate. And bismuth vanillate is chosen as a starting point for the research because it has several good things. It is chemically stable, non-toxic material. And it has very suitable band gap and band position. And this is the band gap, right? Band gap means that the materials has the very good valency band and the conduction band so that it might be able to degrade and treat the materials, pollutants, and also produce hydrogen. And also it has a very good capacity to absorb sunlight. And then the material itself is economical and cost-effective. So with such kind of background, we think that maybe we start with this material for investigation. But then we know that we cannot just use bismuth vanillate directly because it still has some problems, such as the electron, once absorbing the sunlight, the electron excited. But then the bad thing is that it is easier to go back to the valency band. So we call this is a charge recombination. Another drawback of this material is that the surface reactivity is not that high. So that if we want to use this material, we have to do some modification to ensure the charge recombination can be prevented. And also, we have to make the surface more reactive than before. So then this is the modification process to make this bismuth more validate, more reactive. And we so-called this is a reduced bismuth validate, right? And then use that as the photoanode. And then after modification, then we check whether the reactivity is stronger than before. Then we use some sort of XPS spectrum. And then you can see the validate focus before and after modification. And then we have more validate focus. That means the reactivity increase. And then for the oxygen vacancies, before we modification, which is a green color, after that, the oxygen vacancies increase. So that means more percentage of the oxygen vacancies, more percentage of the validate focus. More importantly, and more direct result is that we measure the photocurrent, the electron transfer. And then definitely you can see that without the modification, it is this line in black color. After modification, it becomes the red color, and which is higher current flowing through this material. So then we think this modification might work, and then we can test it. So then we use the batch study, and then for the photoelectrochemical process, the idea is that we use the sunlight, right, to be captured by the photoanode to do the reaction. So to mimic the sunlight, we have the solar light simulator. We can adjust the light intensity, right, mimic the daily sunlight intensity, strong and low light intensity. Depends on the weather. And then we have the reactor, which is called photoelectrochemical reactor. And then we have the, you can see this reactor. We have our material served as photoanode. And then we have the cathode, which is the platinum electrode. And then we have the reference electrode. And then in this reactor, we have the water sample. We take the sample from time to time to see the change of the pollutant. And also, we have the gas sample to see whether we have the hydrogen generate. So we start with this batch study, and then do the two control for comparison. Right, PEC, we have the light illumination, apply the light, mimic the sunlight, and also we apply the voltage. And then we also have the EC, which is electrocatalytic process, just the voltage we apply without the sunlight. And then we have photocatalytic process, just have the sunlight without voltage. So then we can do the direct comparison. And then we take sample, water sample, and the gas sample after treatment. So then this is our finding. Now, as I said at the beginning, we don't use the real wastewater collected in Hong Kong. We just use their simulated water because we're trying to mimic, we prepare the wastewater, trying to mimic the local wastewater. And then based on the local wastewater, the simulated wastewater has the CBZ, which is PPCP. That is a kind of the pollutants, emergent pollutants. And then we also have the equivalent to 300 milligram per liter COD, and also we have 30 milligram per liter ammonia. And then the bacteria in terms of CFU 10 to the power 5 bacteria per mil of wastewater. And the pH of the wastewater is around 7. So in this kind of simulated wastewater, we use it for study to see if it works or not. And bear in mind, I highlight in red color, in this wastewater, we have high chloride concentration, 5,000 milligram per liter. You may ask how come it is high. But do you know that in our Hong Kong wastewater, How high is the chloride ion? Very high, because we use seawater for toilet flushing. So our wastewater usually has the chloride ion over 5,000 milligram per liter. So sometimes 7,000, sometimes 8,000. Occasionally, we might have the 10,000. So using 5,000 actually is the lowest, the concentration of the chloride. So then the result is that, all right, after the treatment by our PEC and the material, and then these are the black and the red color basically is the control, and then the pink color is our PEC system with the modified bismuth validate, and then you can see this pink color. For the PPCP using CBZ antibiotics, and then you can see that how fast we can remove the CBZ to 0. Bear in mind that our 0 point is slightly above that, the origin, because you can see the data point. So then you can see in 5 minutes we can degrade all the CBZ. For the COD, and then in 40 minutes we can remove the COD to meet the treatment standard. For ammonia, nitrogen, in 30 minutes we already meet the treatment standard. For the E. coli disinfection, and you don't see anything, it is 0 because the bar is 0. So just in 5 minutes, we can kill all the bacteria, right? So it's really, really effective. For the hydrogen, we want to generate. So you can see that the pink line is our system. And then the hydrogen generate as the reaction go on. So by this kind of the system, we can see that we have no problem to meet the treatment standard for the Shatin wastewater treatment plant. So then we can continue to see, right, what is the mechanism? How come the reaction is so good, the finding is so good? So then we do some scientific study, and then we conduct the scavenger tests and find out what are the reactive species involved in this treatment system. So then basically, it is the photogenerated host, right, to degrade these pollutants. And then for the hydrogen evolution or generation, it is electron involved, right? Because the electron, the water molecule pick up the electron and generate the hydrogen. And then interestingly, when we have a more and more chloride ion, all right, in the wastewater, as I said, actually, our wastewater has very high concentration of chloride. More and more chloride ions, we will have more hydroxyl radical, which is very reactive species to oxidize the pollutant. And also when we have more and more chloride ion in the wastewater, and then we have more free chlorine, that is chlorine residuals or chlorine species to react with the pollutants. So then we just further test what are the radicals involved. So to remove these pollutants and to kill bacteria, basically we find out that it is the chlorine radicals is the dominant species involving in the removal of the pollutants, followed by the oxychlorine radicals and hydroxyl radicals. So in summary, for the mechanism part, then we truly understand what is going on for this treatment. So for organic pollutants, such as PPCP, COD, BOD removal, basically, it is the chlorine residual and hydroxyl radical involved. For ammonia, nitrogen, it is the residual chlorine, the chlorine or radicals and also oxychloride radicals involved. But then it doesn't produce N2O, it mainly produces the nitrogen gas, N2. For E. coli disinfection, in short time, we can kill all the bacteria. And then for the hydrogen generation, on the cathodes, we generate the hydrogen, and it is the electron involved. So then, understanding the mechanism, then we can apply the real wastewater to see whether it works rather than the simulated water. So then we collect 2 wastewater from local treatment plant. One is the Shatin, the other is Stonecutters. Then you can see the color is still different because in ZHANG, it is biological treatment. In Stonecutter, it is chemical enhanced treatment. So then we measure before we the treatment, and then we measure the quality of the wastewater. And then compare with our simulated sewage we used previously. So then you can see that for the chloride ions, and then the ZHANG has much higher than the chloride ion, than Stonecutter, and even higher than the concentration we use in the simulated sewage. So we test this real wastewater, and then after our PEC technology, you can see the picture. That is from ZHANG, and then after treatment, it is very clear. And this is from Stonecutter. After treatment, then you can see that the treated wastewater is much transparent. And then we measure all those parameters, concentrations, and then we have no problem to meet the treatment standard. So we meet the discharge standard. Basically, we can discharge to the water body without problem. So then we are excited because so far the technology in the laboratory scale, small, and in the batch scale, right? So how can we turn it into the real application for the practicality, right, use? So we have to think about the upscaling of the batch reactor into a large scale reactor. Batch means that we just have the certain amount of wastewater to be treated. No inflow, no outflow. But for the continuous flow reactor, right, that is large scale reactor, we have the inflow and outflow continuously to treat the wastewater. It is totally different scale. And then we have to think how we can design the reactor, changing this kind of batch design into a continuous flow design. So then we talk to different manufacturers and engineers, and then think about the design and also our criteria. So our criteria list all here because we have to make sure, right, the system should have the sufficient contact point of the photoanode with the wastewater. And also we have to maximize the sunlight absorption because we basically use the sunlight, right, to do the reaction. So we're also trying to make sure all these pollutant in the wastewater will be well mixed without any dead zone. So all these criteria, right, we decide, and then we talk to the manufacturer. And then at the end, we come up this design. And then this is the continuous flow reactor. And then you can see that, all right, there's different components. So you might just watch this video, and which is 2 minutes only, then you can see how it works.
Without further ado, let me give you a tour to see our real PEC reactor. We have dedicated our efforts to design this large-size PEC reactor. It consists of 5 major parts, including the PEC cell as the key components, the electrochemical workstation, pumps, influence and effluent tanks, and the control panel. Our PEC system is made out of 9 top-fixed photoanodes, which maximizes the surface area and the sunlight absorption ability of the photoanodes. At the same time, 9 cathodes are placed at the back of the reactor as well. The sewage to be treated is coming from the influence line at the bottom, while the effluent comes out from the top effluent line. The bottom-up flow design can effectively prevent the formation of dead zones and ensure proper mixing in the reactor. To start the operation, we turn on the reactor by the control panel, and then we can conveniently adjust the applied current, voltage, and flow rate of the circulation pump to meet our designated conditions. At a regular interval, we take effluent samples from the reactor and monitor the concentrations of various pollutants, such as ammonia-nitrogen, chemical oxygen demand, and bacteria. Other than wastewater treatment, our PEC system can also generate green hydrogen as fuel. You can see that hydrogen gas bubbles are evolving vigorously from the cathode, in which they will enter the effluent tank along with the treated effluents. To detect the hydrogen and greenhouse gases generation in the PEC system, we are also collecting gas samples regularly. Here you can see a direct comparison between the raw sewage and treated effluent. Apparently, the water has become significantly clearer after the PEC treatment, and the quality of the effluent can meet Hong Kong's discharge standards. To reach round-the-clock operation, LED lamps could be equipped to the reactor as a supplementary light source to provide sufficient light intensity for PEC reaction during nighttime.
Okay, so here is our reactor, and then bear in mind that this reactor, we have the lamp built in. In daytime, we use sunlight to treat wastewater. In nighttime, we have the LED lamp. And LED lamp can be supported by our solar panel or just using electricity. So then this is the result. Again, without any problems, we can treat the COD to meet the treatment standard. We can remove ammonia nitrogen to nitrogen, right? We can kill the bacteria in short time, right? 2 hours retention time. And then hydrogen, right, generation increase over the time we treat the wastewater. So on average, every cubic meter of wastewater we treat, we can produce almost close to 1 kilowatt hour, right, electricity. And then we have no problem, right, to kill the bacteria to meet the treatment standard. And then you can see that using the real wastewater we collect from Stonecutters, and then after treatment, we can meet all these parameters standard, and this is the color before and after treatments. And then not only this, we make sure that wastewater, right, might have some fluctuation from time to time. So over the last years, we collect different samples at different time periods. So in May 2024, October 2024, April 2025, May 2025. So the wastewater, right, have some fluctuation. For example, the COD variation might be around 18%, and ammonia nitrogen varies 31%, and then total suspended solid 48%. So although the wastewater is not, right, always stable, but with some variation. But in terms of the treatment after our PEC, right, degradation, and then we can still meet the treatment standard. So regarding the greenhouse gases, we say that it is a low carbon emission. So we collect the gas and measure. So compare with the conventional wastewater, right? The orange color is conventional of the generation of methane gas and N2O. But after PEC treatments, you can see that you almost cannot see any CH4 with a little N2O because most of the ammonia nitrogen turn to nitrogen gas. And then for the hydrogen we generate, all right, for every liter of the wastewater we treated. So in total, okay, it is the reduction, right, a substantial reduction of ammonia, of the methane gas and N2O, and also we produce substantial amount of hydrogen gas. So then in terms of the greenhouse gases, we do the two scenarios, as you see. If we don't use solar panel for nighttime use to support the LED lamp, assuming that in daytime we use the solar light, nighttime we have the lamp to support the reaction. So then compare with the conventional, all right, wastewater. We have the scope 1, scope 2, and total. Total basically is the summation of the scope 1 and scope 2 and offset. So the total emission from the conventional is much higher than our total emission from our technology. We can claim that it is nearly net zero process. But if we really consider the use of the solar panel to support the LED lamp in nighttime, then the total emission is negative, right? Because we produce hydrogen, right? That is positive. That is energy that can offset the carbon emission. So if we consider using the solar panel, then the total emission will be even negative. Negative means that we can sell the carbon emission for carbon trading. So I use this data to illustrate the socio-economical value of our technology, assuming that we use this technology for the Stonecutters Island treatment, which it treats 1.4 million cubic meter per day. And assuming that for carbon trading, all right, we can, every tons of carbon emission you reduce, you can trade $160 US. And then assuming that we can turn the hydrogen into electricity with certain efficiency, 30%. So then every mole of hydrogen, we can generate this kilowatt hour. So then you can see that every year, we can reduce 300,000 tons of carbon for Hong Kong, right? And it is important because Hong Kong, just from the wastewater treatment, we produce 3% of the total carbon emission already. And then we can use the negative carbon emission, right, to generate money for carbon offsetting or carbon trading. And then using the hydrogen to generate the electricity, it will be able to support 100,000 households. So if you remember, for the incineration, we will have the incineration plant at the end of this year or early next year. 3,000 tons of the solid waste burning, right, and generate energy from our new incineration plant. Then the total energy we produce will be sufficient to support 100,000 households. Exactly the same as this technology applied for the Stonecutter wastewater treatment. Again, we can produce the same electricity. So then, actually, other than the original form of the reduced bismuth validate, our research group keep improving this material. And then we further revise or modify this material into oxygen vacancies, iron oxide bismuth validate, and the performance even better and faster. And then this is the data to showing that how good is this newly materials. We keep improving the performance and then the lifespan of this material so that we can use it for longer time. So then finally, it is the summary. We developed this multifunctional PEC system. I can say that one stone kills 5 birds. The first bird is to comply with the treatment discharge standard in Hong Kong. Second bird is that we use solar light to remove pollutants through the PEC system and reduce the greenhouse gases. And then the third one is that we use solar light at the end, we can turn it into hydrogen fuel. And then for the wastewater, the conventional wastewater cannot remove antibiotics, PBCP, but our system can. It is a bonus. And the last one, that our system can kill bacteria as well. We don't need to add chlorine for chlorine disinfection. No chemical addition is needed. And no worry about the formation of disinfection byproduct, which is cancer-causing material. So then this also the last slide we got last year. We have the international net zero technology for environmental application. And it was held in Taipei. And there were 200 entries, more than 200 participants. And then we are lucky we got the first one up, all right, for this international contest. And also thank you for Drainage Service Department. And they actually provide the support, financial support to do this research. And also the Government Research Grant Council to provide their financial support for early stage research. And then this is our publication, and this is Hong Kong USD. All right. So thank you very much for your attention.